Hello and welcome to the second in the series of our Introduction to Synthesis. And today we're looking at oscillators. And oscillators are the things that actually generate the sound in a synthesizer. So as we've talked about before, an acoustic instrument generates sound by some means of vibration. That could be a vibrating string, a vibrating skin on a drum, metal on a bell or mallet, etc., etc. And timbre is another concept we have to get our head around and we'll look into today. And timbre, also known as tone, or is the nature of the sound of the instrument. Why can you have two acoustic guitars and they sound different? It's because they have different timbres, and that is something that is related to harmonics and also formants and enharmonics. And we're going to have a look at that in a little more detail as we go through this presentation. So quickly, the harmonic, the first harmonic, is also known as the fundamental or the root note, and that is measured in frequency, which is hertz or kilohertz. The only note out of all the musical notes that has an exact number as its frequency is the note A. So A can be sounded at 440 hertz. And if you have a guitar tuner and you have a look, it will probably give you a rating for A440. That's what the 440 means. 440 cycles, a cycle being a positive air pressure, negative air pressure. There's one cycle per second. Now, the harmonic series actually is a little bit of physics and mathematics. And what that says is that if I play this note, a fundamental note, one octave above it, which is 2 times 440 hertz or 880 hertz, which will sound an octave higher, is the second harmonic. There's a third harmonic, which is 3 times 440, 4 times 440, 5 times 440. These are known as the harmonic series. So here is half my waveform, and then the second harmonic has 2 in that space. The third harmonic has 3 in that space, 4 times the amount, 5 times the amount. And amazingly, they all have a musical relationship to each other, which we'll look at very briefly as we go through this presentation too. Now, samplers we looked at in our first lesson, and what is the difference between a sampler and a synthesizer. And the fact is that sampler plays back an audio recording of a sound, whereas a synthesizer electronically generates the sound. And our topic today, oscillators, is the means by which a synthesizer generates the sound. So there are many different types of synths. There's subtractive, additive, frequency modulated, granular, and other types as well. But within the scope of our course, which is a basic introduction, we'll come back to our Olympic rings here and the 5 basic components of a synthesizer. In our first lesson, we looked at the envelope filter down here. This week, we're coming back to the very foundation, the oscillators. So an oscillator is the foundation of the synth. It generates the original sound, which is then filtered and affected to produce different timbres. So we remember at this point that a synthesizer does not create sound through vibration. Early synthesizers created sound through the means of electricity and oscillators, and later synthesizers do the same thing but do it digitally. So an oscillator is what's generating the sound wave. The sound generator is built on the most basic type of waveform, which is a sine wave, and we're going to have a look at that. A sine wave has a fundamental tone but no harmonics, enharmonics, or formants. No acoustic instrument can produce a pure sine wave. A sine wave does not exist in nature. Oscillators can be voltage controlled, VCOs, or digitally controlled, DCOs. And with a VCO, a music keyboard in a synthesizer pushes various voltages through the oscillator, which generate different frequencies. With a DCO, this is controlled through software. Now, a lot of this is probably gobbledygook at the moment, but as we demonstrated, it should start to make more sense. In terms of wave types, as we talked about earlier, the basic building block of all synthesis is the sine wave, which has only the fundamental note. It's very electronic sounding, very clear, very pure, kind of gets in your head in a bad way. Now, all other wave shapes come from combining sine waves, and the summing or cancellation of frequencies when the new sine waves are added produces new timbres. So you will be seeing things like square waves, sawtooth waves, triangle waves, and within this PowerPoint you'll be able to read the nature of all of those particular types of sine waves. Now, I'm in Logic and I have a few different software synth tracks created, but on this particular one I've inserted an audio effect called the test oscillator. I'm going to use the oscillator to generate a sine wave frequency at 1 kilohertz or 1000 hertz. Now I've turned this down so hopefully it won't blast your ears too badly, but here we go, we'll turn it on now. And we'll have a look at the EQ and we'll make sure the analyzer function is turned on. And there I can see that here is my frequency, 1 kilohertz, and that's all there is, just my fundamental frequency and no other. Now we'll have a look at a square wave and see the difference, and what we'll start to see with a square wave is that it contains part of the harmonic series, and we will hear that the sound is a little bit different to the sine wave. So let's turn on the generator and have a look at the EQ. So here is my harmonic series. It's actually missing the second harmonic. It's got the third, it's missing the fourth, it's got the fifth, seventh, so it's got all of the odd harmonics. That is the harmonic series that we looked at earlier in the presentation. So here is my fundamental. It missed the second harmonic, which would have been double the frequency, but it included the third. It missed the fourth, but it included the fifth, etc., etc. Now this starts to introduce us to the concept of the harmonic series and the fact we can see it visually. When I'm reading this EQ, by the way, I start here at 20 Hertz and go all the way up to 20K. That's the limit of human hearing. So along the horizontal axis is frequency or pitch, and along this axis is volume. So when I hit my note, I can see the note 440 has the strongest volume, and the harmonics above it all have different amounts of volume, and they're all fading away. What I'm going to do now is I'm going to play the same note A. I'm going to play it on an electric piano, and we will see that the harmonic series is a little bit more complicated when you have a sound that's not electronically generated. So I'll just hit that note now. And there you can see my fundamental frequency is 440, but we can see that that's going down, and the harmonic series above it, you could see it had at the start quite a strong prevalence of the second, third, fourth and fifth harmonic, but all in different amounts. I'm going to change the sound on this electric piano, and let's have a look how by changing the sound I'll get a different harmonic series. We can see up in this area a different prevalence of the harmonics, a different strength. Let's now have a look at some of the Logic synths, and here I can see my oscillator section, and these symbols all represent different types of waveforms. So I have my sawtooth wave here, and I'm going to hit that note. Now I can see that over here I've got a no sustain, so that note is disappearing very quickly. And while I do this, I'll also pull up an EQ so we can see the effect of that on the harmonic series. Here we go. So very strong on the fundamentals, quite like a sine wave, but has a few of the harmonics above it. Next. And you can hear it's a very different tone, and this particular tone includes some of the even harmonics there. Here we've got a square wave. And again we can see the odd harmonics coming in there. And then these ones, where you see the -1, it is the like the square wave, but includes the note down the octave. And the -2 includes the note down 2 octaves. And noise is the same as white noise, and what we'll see with noise is that it is all frequencies without any one frequency being louder than the other, and therefore we can't define a pitch from it. All we hear is noise. You can see all the frequencies in the analyzer coming through there. So here I have a synthesizer. Here is an oscillator section. These numbers to the side are to do with the pitch, and of all things, the numbers represent pipe lengths, which harps back to the old days of cathedral organs with their massive pipes. So the longer the pipe length, the deeper the note will go, and this will decrease by an octave. So here's an A. Here's the same note. I'm playing exactly the same note on the keyboard. And you can hear that that's an octave lower, etc. Now let's have a look at a couple of other synthesizers. So I'm still in Logic. Here's the ES1 synthesizer. And now I can see I've got two oscillators, and I can mix between the top oscillator and the bottom oscillator. And I can select through waveforms, square wave, sawtooth, triangle wave, and then this type of square wave, but uneven in its modulation. And this one is a sub-frequency, so I can blend elements of sub-frequency. And again, if I have a pure square wave and I turn my EQ on for this and the analyzer and I play my note A440, you can see that that is a much more complex waveform in terms of the harmonics and other notes connected with that. And that's why the tone or sound quality is different. Again, I have my pipe lengths or my octave basically controller over here. And I have an ADSR section over here, which we looked at last week. Here's another synth again, the ES2, and now I can see that I have three oscillators and a little bit more choice here. This one includes a pure sine wave up here, as well as my square waves and a sawtooth and triangle waves. Or here's my sine wave down here, pure sine wave. I have another oscillator that has those, but a few more variations. And I have a third oscillator. And then with all of these, I can choose how much of any one of the particular oscillators I'm hearing. So let's have a listen to the sound. And I also have the ability to tune them in octaves, etc., etc. And over here, I have three sets of ADSR controllers with a couple of extras added in, and they apply to each of the envelopes. So this is like my AD, well, it only has AD, not S and R. That applies to oscillator 1. This one applies to oscillator 2, and this one applies to oscillator 3. So hopefully we can start to put together at least a little bit of an insight when we look at this synthesizer as to what the components are and what they're doing. I would always suggest when you're looking at new plugins, whether that's for audio effects or software, that you just start by going through your presets and finding stuff you like, and then having a look at how those settings look so that you can start to get an idea of the power of the synth. So the job today is to go and open a bunch of synths and see if you can identify the oscillator section and the ADSR section in those synthesizers and have a play with them and see what kind of results you get.